All right, so this presentation will go over electron configurations. I'm anticipating that it's going to be a little bit long just to get through all the things, but hopefully it will all make sense. So our objectives: we'll review quantum numbers and what they physically refer to. We'll define electron configuration, condensed electron configuration, and orbital diagrams. We will then relate quantum numbers to the periodic table to systemize writing the electron configurations, condensed electron configurations, and orbital diagrams. And finally, we'll practice writing them because you always need practice to make this make sense. So last time we talked about atomic orbitals being a solution for the probability function that is the Schrödinger equation. This time we will talk about the rules that govern where electrons can go in what orbitals. The principal quantum number gives the relative size of the orbitals and the shell. The secondary quantum number gives the shape of the orbital. So we have the S, the P, the D, and the F. Now, we will often write things like 1s, meaning the principal quantum number is 1. The secondary quantum number corresponds to the s orbital, which is that sphere, and in that case, L equals 0. So let's review our quantum numbers. We have the principal quantum number, or n, which is an integer, meaning counting number 1, 2, 3, 4, etc., that designates the size of the orbital and the shell. N is equal to the number of radial nodes, which in the last presentation I called spherical nodes, but Active calls them radial nodes, so I'm trying to clear up confusion that is definitely going to happen as a result of that. Angular momentum, quantum number, or secondary quantum number, cursive looking L, is the subshell, and it gives the shape of the orbital. So for this, S is equal to 0, P is equal to 1, D is equal to 2, and F is equal to 3. The secondary quantum number corresponds to the number of angular nodes, which I called nodal planes in the last lecture. Same idea. L can be 0 to n minus 1. Them's the rules. The magnetic quantum number, or m sub L, is the orientation of the orbital in space. M sub L can be given by negative L to positive L, including 0. So you determine the number of degenerate orbitals for a given L by using the m sub L. And finally, we have the spin quantum number, or m sub S, which refers to the spin on the electron. It can be plus or minus 1/2, so plus 1/2 or minus 1/2. It is represented as spin up or spin down, and we'll get more on that later. So let's try to apply these rules. Which of the following is physically impossible according to our quantum number rules? So on the bottom right-hand side, we have a summary of what we can do, and we have a bunch of different orbitals. So I want you to pause here, see if you can figure out which ones are allowed and which ones are not. Okay, so for 3F, 3 represents N and the F represents the L. N is 3 and L is 2 because F is 3 because F corresponds to the L equals 3 orbital. Since L can only be 0 to n minus 1, and n is 3, n minus 1 is 2, L of 3 is not allowed. Right. In the second one, we have 1 for the n, L is 0, which is allowed, m sub L is also 0, allowed, and plus 1/2 definitely allowed. Then we have 3, 1, negative 2, negative 1/2. So our n and our L are okay, but when we go to the m sub L, it can be negative L to positive L, and our L was 1, so it can go negative 1, 0, 1. That does not include negative 2. This is not allowed. That's not an orbital. We have 2, 2, 0, 1/2. When n equals 2, L can be 0 or 1. So this is not allowed. With 7s, n is equal to 7, L is equal to 0. That's fine, perfectly allowed. And finally, we have 1, 0, 0, 1. That last quantum number should be plus or minus 1/2, and it's 1, so that is not allowed. Okay, when we fill atomic orbitals, we're going to follow the off-bell principle, which means to fill the lower energies first. And we determine which energy is lower, either by using this fun list of orbitals with diagonal lines through them, or by using the method I'm about to show you with the periodic table. Hund's rule says we fill degenerate orbitals each with 1 electron before doubling up. And by convention, we're going to go with an up arrow when we start. And finally, we have the Pauli exclusion principle, which says no two electrons can have exactly the same quantum numbers. Things can't be in the same place at the same time. So let's try to fill in some orbitals. Let's start with electron configurations. We're going to do something stupid easy, helium. So what is the electron configuration for helium? Well, first we need to know how many electrons we have. Z is equal to 2, so there are 2 protons, and we have no charge, ergo there are also 2 electrons. So according to the off-bell principle, we should start with the lowest energy orbital, which is the 1s orbital. Okay, we have 2 electrons, and we can fit 2 electrons into each orbital, so we're going to have 1s, and then we're going to put in a superscript 2. So when we write electron configurations, we're going to have the principal quantum number. We're going to put the angular momentum quantum number as a letter, S, P, D, or F, and then we're going to have a superscript for the number of electrons in that orbital. S orbitals can contain 2 electrons. P orbitals can contain up to 6, D orbitals up to 10, and F orbitals up to 14. All right, so let's do this again with the electron configuration of lithium plus. Now, I am including an ion so that we can get a chance to do the thing where we count again. So Z equals 3, and normally that would mean 3 electrons. But we have a +1 charge. So 3 electrons plus 1, right? 3 times -1 is -3, plus 1 is -2, so there are 2 electrons. Well, from there, we know we're doing 1s and we're doing 1s2. These 2 things, helium and lithium plus, are isoelectronic, meaning they have the same electronic configuration. Now, we talked about isoelectronic ions earlier in the term, and we were learning about ionic compounds. The most stable ion is the element that is isoelectronic with the closest noble gas. So whatever the element is, if you make it into an ion, it will be most stable when it has the same configuration as a noble gas. So when we start adding more electrons, we'll need to remember the ranking from the previous slide. And I told you I would teach you a different system, and we're going to use the periodic table because that's the way that I find it easiest, because literally I just count. So here we go. This is how I remember the rankings. Okay, so if we outline in red the alkali metals and the alkali earth metals, we're going to call this the S block. And the main group elements we're going to call the P block. The transition elements we're going to call the D, and the rare earth elements we're going to call the F block. So with the F block, the D block, the P block, and the S block. If you look in the bottom right of this periodic table, you can actually see them labeled as a monolithic color. So red for S, yellow for P, blue for D, and green for F. We actually do refer to things as being in the D block or the F block or the P block when we're talking about elements. So if you ever hear that said, you know what region of the periodic table we're referring to. The outermost electrons, the ones that are in the highest orbitals, are considered to be in the valence shell. They are called valence electrons. Valence electrons are available to bond, so they're super important. Now, everything else is called a core electron. It's in the center. Of particular note, when you look at how I have arranged this, I have written 1 through 7 from top to bottom. Those refer to the principal quantum numbers. For the S block and the P block, that is straight up what it is. But for the D block and the F block, we actually have different numbering for the principal quantum numbers. So the D block will start at 3 and go up, and the F block will start at 4 and go up. You need to remember that if you're going to use this method, or you will get configurations wrong. So again, D block starts at 3, F block starts at 4, and all will be right with the world. This order has been confirmed by experimental and theoretical calculations. So this is not whimsy, this is what we actually observe. So let's try using the method that I'm about to show you. Okay, so let's say we wanted to do the electron configuration of boron. Boom. We start over here. We have 1s, 1, 2, 1s2, 2s, 1, 2, 2s2, and we're going over here to boron. So we have 2, still in the 2 row, p, and there's 1 electron. So I am using these labels, and then I am literally just counting across until I get to the number of electrons I want. All right, so let's give some things a try. What if I had lithium? Over here, it's an alkali metal. I would do 1s2. So start with hydrogen and helium, that's 1s, and there's 2 of them. And then I go down to the next row, and I have 2s, and there's 1. I go 1 across, so it's 2s1. What about chlorine? Chlorine's all the way over here. We've got 17 electrons. And so we just start counting. 1s2, 2s2, 1, 2, 3, 4, 5, 6, 2p6, 3s12, 3p, 1, 2, 3, 4, 5. So it'll be 3p5. Okay, we continue onward. Let's try lead. Whew, lead has a lot of electrons. Let's see if we can find where that is. 82 of them, in fact. Okay, so we would start counting. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then this is where it gets weird, 3d10. And then this is 4p6, 5s2, 4d10, 5p6, 6s2, 5d10, and then we're in 6p12. That was admittedly a lot, but again, all I did, label things and count across. Which finally brings us to neodymium. Neodymium is a rare earth metal, so we are going to have a lot of electrons, but not as many as lead, ironically. So there's 60. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then we go down to the F. 4f. 1, 2, 3. 4f3. Okay. We can't forget that we have to go down to the rare earths once we hit the 4. Okay, so that was kind of obnoxious. We recognize that that's obnoxious, and so we came up with a shortcut. All right, so that was kind of obnoxious. We have a shortcut because chemists don't like to do repetitive and obnoxious things, so we summarize them. We're going to put all of our core electrons, and we're going to say the closest noble gas. It's completely full. That will represent all the core electrons up to the thing. And then we're going to count on from the noble gas and just put the valence electrons. So we'll have the noble gas in square brackets, and then we'll have the valence electron configuration from there on. So let's try to do that. So let's start with manganese. Manganese is right here. There's 25 electrons on manganese. If we go back in time, the closest noble gas with a lower number of electrons is argon, and there's 18 of them. So we put argon in square brackets, and then we go back and we start counting from there. 1, 2. This is 4s2, and then we keep going. 1, 2, 3, 4, 5. 3d5. 4s2, 3d5. That was way easier than putting all of the core electrons in. So let's try another one. Holmium. Where the heck is holmium, right? When do we ever use that sucker? So, all the way down here, it's a rare earth metal. Okay, so this is going to be in the 4F. So 67, the closest noble gas to 67 that is lesser is xenon. So we're going to put xenon in brackets, and then we're going to go over here. 1, 2, 3, 4, 5, 6, 6s2, and then we go down, boom, 4f, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 4f10. Let's try oganesson. That'll be fun. Turns out oganesson is a noble gas. We just put it in square brackets, and that's it. We call it a day. And finally, FL. So that's a new one. We got 114. And this is just conjecture because we don't actually know the electron configuration of this. We haven't studied it. But we would put radon in square brackets, and then we would count from there. So we're on 1, 2, 3, 4, 5, 6, 7. We're in the 7th principal quantum number here. 7s2. Then we go down here. 5f10. And we go back up here. 6d all the way across 10, or sorry, 5f14, 6d10, and then we have 1, 2. So this would be 7p2. All right, so that was a bit of a trip, but hopefully not too bad. Which brings us to the orbital filling diagram. What are these suckers? We're going to fill the boxes according to Hund's rule and the off-bell principle for silicon. So the first thing we have to know, how many electrons does silicon have? So we look at our periodic table, and our periodic table tells us that silicon has 14 electrons. So we're going to start filling these. And I would like you to try. Now, there's two things that you need to know. So for Hund's rule, it says we fill degenerate orbitals 1 electron at a time before doubling them up. And the second thing is, by convention, we always start with spin up when we're filling. So I want you to go ahead and try to do this on a piece of paper. We're going to show the answer next. All right, so when we filled in our boxes, we did 1s2, 2s2, 2p6, because we're going lowest energy to higher energy. That gets us to 10. Then we go 3s2, that gets us to 12, and we have 2 left over. We're going to follow Hund's rule, and we're going to put 1 in each box. And you may be wondering, this is tedious. Why am I filling a bunch of boxes? It turns out this stuff comes in handy for explaining periodic trends in the next presentation. So we need to learn how to do it so we can understand other things. For now, let's talk about some weirdness that is going to be illustrated by orbital filling diagram. The D block does weird shit. Like, very weird. So if you write the condensed electron configuration for copper plus, it is argon 3d10. It is not 4s2 3d8. But why is that? That doesn't make any sense. We just said that we're going to go and use the off-bell principle, and we're going from low to high, and we're filling a higher orbital first instead of the 4s. So here's what that is. So I have the 2 different configurations using box diagrams of just the valence electrons. It turns out exactly half filled or completely filled orbitals are more stable than a mix and match situation. So in the top here, we have a completely filled d orbital. That's a 3d10, where everything is matched, and we have nothing in the s. If we were to fill the 4s first and then go and fill the 3d, you notice how we have 2 electrons by their lonesome. We have a mix of paired electrons and electrons by their lonesome, and they are not happy. That is not the lowest energy state that you can possibly have. It is more favorable to have electrons matched than it is to have them partially matched and completely matched. So let's do another example. Write the electron configuration, the orbital filling diagram for 4s and 3d for chromium. So just do the valence electrons. Favor the configuration where you have half-filled orbitals. So I want you to go ahead and write that out. So if we do chromium, we know that we have 6 electrons after the argon. I get that just from counting. And if I favor half-filled orbitals, then I put 1 in the 4s and 5 in the 3d. I have 4s1, 3d, 5. And that is weird. That's not what we expect, but that is the most stable configuration. Now, exceptions like this are true for the entire group. So for copper, silver, gold, röntgenium, all of them will have that same configuration where they completely fill the 3D. Chromium, molybdenum, tungsten, and seaborgium will all have this situation where everything is half filled, including the S. There are a few more exceptions that occur at higher Z values, but they're hard to predict. Know that they are in existence, and we'll call it good. I am not going to make you know them. I will make you know the ones for the copper and the chromium columns. Okay. There's a periodic table in your textbook that has all the condensed electron configurations of the elements that are known. If you want to check that out, if you're curious about it, just look up the exceptions there. So we call the outermost electrons the valence electrons. The valence electrons are available to bond. All other electrons are called core electrons. Electrons go into atomic orbitals, and there are rules for filling them in, but you can fill those orbitals using the help of the periodic table as a cheat sheet. An electronic configuration is the way the orbitals are filled for a given element. So for example, carbon is 1s2, 2s2, 2p2. We use the principal quantum number, the secondary quantum number as a letter, and then we give in a superscript the number of electrons in that orbital. A condensed electron configuration is done by taking the closest lower electron noble gas to represent the core electrons and then counting up from there. So we put the noble gas into square brackets. So for sodium, that would be neon, and then we count on. We have 2s1. Our orbital filling notation uses boxes to represent orbitals. All the electrons start spin up, and then you put them in spin down using Hund's rule for filling the orbital. And finally, when you're filling s and d electrons, half-filled and completely filled orbitals are more favorable than some half-filled and some completely filled, which leads to weird exceptions for the column with copper and the column with chromium.